So let me go over the sequence of events now that constitutes inflation. The previous slide was supposed to explain essentially the underlying physics. But inflation proposes that a patch of repulsive gravity material existed in the early universe. And if inflation took place at the grand unified theory scale, as there's now some evidence for coming from the discovery of gravity waves, which I'll be talking about later, then this patch, the grand unified theory scale gives us the numbers, this patch would really only need to be about 10 to the minus 28 centimeters across to be large enough to ultimately become our entire observed universe. This, by the way, is more than 1 billion times smaller than the size of a single proton. So we're really talking about an amazingly small size for the piece of space that's going to ultimately become the entire observed universe. Now, since any such patch is enlarged fantastically by inflation, the initial density of such patches, or the probability of such patch forming in any given location, can be very low, and it doesn't really matter. As long as it eventually happens, it then becomes the entire universe, and possibly even much more. So the assumption is then that the gravitational repulsion was the driving force behind the Big Bang, and this gravitational repulsion causes this tiny patch to start to grow exponentially with a time constant of about 10 to the minus 38 seconds. So every 10 to the minus 38 seconds, this little patch would have increased in size by a factor of e, the base of the natural logarithms. So what we need is for this initial patch to expand exponentially by a factor of about 10 to the 28, which involves about 100 doubling times, 60 time constants, or 60 or 70. But it could have expanded much more. There's nothing that needs to be fine-tuned about the amount of expansion. There's a minimal amount needed to explain what we see, but there could be vastly more expansion, which would just mean that the region that we're living in is vastly larger than what we have been able to see. In any case, at the end of inflation, the size of the region that will ultimately become our observed universe would have been about the size of a marble, about a centimeter or so across. And then at the end of inflation, the acceleration turns off, but this little marble-sized region is still expanding, and it continues to expand and coast, starts to slow under the ordinary force of gravity at that point, but continues coasting right up until the present day. Now, what ends inflation is that the repulsive gravity material is unstable, so it decayed pretty much like a radioactive substance decays. That is, the decays are just random. There's no way of predicting where or when a decay will take place. But when the decay does happen, the energy that has been locked up in this repulsive gravity state gets released and becomes a hot soup of ordinary particles, which is exactly the starting point of the conventional Big Bang theory. So inflation plays the role of being the prequel to the conventional Big Bang description. Now, there's a very important feature here which needs to be explained and leads to the second miracle that I want to talk about, which is that during the exponential expansion, if we were talking about ordinary matter inside this region, it would thin out by a fantastic factor because it's expanding by a factor of 10 to the 28 linearly. That means 10 to the 76th in volume. So the density would fall by that incredible factor if we had ordinary substance inside. But it turns out that this repulsive gravity material actually does not thin out at all during the exponential expansion, which seems like it's going to violate conservation of energy because we have a fixed energy density and the volume is expanding by a colossal factor. So how can that be consistent with energy conservation? Obviously, this is a place where we need another miracle, and it's coming up. The miracle is not any violation of energy conservation. Energy is rigorously conserved as far as we know in all cases, and this inflation theory would not fly if it violated energy conservation. But what protects it is the peculiar feature that the energy of a gravitational field is actually negative. Now, this is a fact that's true even in Newtonian gravity, and it's also true in general relativity. For some reason, though, it's never become a well-known fact about physics, except maybe recently, which is why I'd classify this as a miracle. It's certainly nothing that anybody taught me through the time I got my PhD. And the way it works then is that the negative energy of the gravitational field that fills this region as it exponentially expands cancels the positive energy stored in the matter so that the total energy can remain constant and possibly exactly equal to 0. So the bookkeeping is shown here. The total energy is the matter plus radiation, which is in black, positive. The gravitational energy is negative, so it's shown in red as in a financial ledger. And it all adds up to about 0. And that means that this expansion could go on literally forever without any problems concerning energy conservation.